Okay, a very warm welcome to all of you. We were talking about parallel operation of single phase transformer. In this lecture, we are going to talk about on load operation when there is unequal voltage ratio of transformers. So under this condition, that is unequal voltage ratio, we have seen that this unequal voltages are EMF that is going to rise the circulating current on no load. So when load will be there, when a load is connected in transformer, at that time the transformer is going to share the load current in proportion to their kVA ratings, which is going to further depend upon their leakage impedances. Here the resultant current that is equal to the phasor sum of the circulating current and the load current. So for this case, here is the phasor diagram. You could see the phasor diagram, and here what we have assumed while drawing this phasor diagram, that the EA and EB are in phase, and also we have assumed that EA is greater than EB. So the load current I, which is to be shared equally by transformer, this load current that will lag voltage by load power factor angle theta 2. Since we have assumed that EA is greater than EB, so the current shared by transformer A, that will be the phasor sum of I by 2 and IC. We said that the load current I to be shared equally by transformer, that's why we have considered here I by 2. So it is I by 2 plus IC. What is IC here? IC is circulating current. IC is here circulating current, and the I by 2, that is the current which will be shared by transformer A. So total current, that will be the sum of I by 2 and IC. The total current shared by transformer B, that will be the phasor difference of I by 2 and IC. So the IB, that will be given by I by 2 minus IC. You could see in phasor diagram we have shown in that way. You could draw V, you can take V as a reference, and I that can be drawn at an angle of theta 2. So it is lagging by this angle theta 2. I is lagging V. So you could basically get this circulating current, the current which is shared by transformer A, IA, and the IB. So IA and IB, that will be basically your half of I by 2. So where you will get half of I, that will be here, and your IC, that will be this one. So basically this is phasor difference. When you are going to take I by 2 and IC, you are going to get IB, and when you are going to take the phasor sum of I by 2 and I, you are going to get IA. So it's phasor sum that is going to give you IA. This is your basically the resultant current. So here you could obtain, once you are having the current which is shared by transformer A and transformer B, so you are in position to draw the EA. So the drop, when you will add the drop into the V for transformer A, you are going to get the EA. So what we have done in V, the IA ZEA drop, leakage impedance drop, that is added. So we are getting EA, and when you are adding IB ZEB in V, you are going to get the EB. So EA minus EB, that will be given here. Earlier what we have seen, the angle between these two, that will be given called as the beta. So what we will do here, we are going to consider its equivalent circuit. Already we considered in previous lecture. So the same circuit we are going to use here, and we are going to write the mathematical expression. So we will apply KVL in this loop, and we'll find the first expression equation like this: EA minus IA ZEA, which will be equal to IA plus IB into Z. So you just apply the KVL here, you are going to get this expression. And similarly you can apply the KVL into this loop, so you are going to get this expression: EB minus IB into ZEB, which will be equal to IA plus IB into Z equal to V. So basically EB is here, this drop is added, then this will be equal to this Z into the current which is flowing into this load. So the current which is flowing, that is Z into I. And what is I? I is nothing. You can apply here KCL, so you'll find out that I is equal to IA plus IB. So we have written in this form, IA plus IB form. Instead of that, if you want, somebody wants, you can write that in I form. This is written intentionally. So what we will do, our intention is to determine the value of IA and IB, the current which is shared by transformer A and the current which is going to be shared by transformer B. So what was the assumption here? We have assumed that the EA is greater than EB. We will continue with that assumption, and we will try these two equations, that is equation A and B, that will be solved. So what we will do, we are going to subtract A from B in order to determine the value of one of the current. So here we have subtracted, and from this we could either determine value of IA or IB. So here we are going to determine the value of IB. So IB can be determined, so it will be given by this expression: IA ZEA minus EA minus EB divided by ZEB. It is quite simple. What you need to do, just IB has to be calculated. So you can take this IB on this side, and EA minus EB, that can be taken on this side. So this IA ZEA minus EA minus EB you are going to get, and this ZEB will come to denominator. So IB is calculated. So what you can do now, you can substitute this value IB in this expression A. So you are going to get this value. So just to substitute the value of IB in the expression A, then do little bit simplification, you are going to get this expression. Now this expression, from this expression our intention is to determine the value of IA. So just to simplify it, and you can get the value of IA. So this will be your IA. We have written this expression into two parts. So here the second part, it is showing the circulating current. So this is indicating circulating current in transformer A. So this would be the value of circulating current. So similarly, on similar basis, what you can do, you can calculate the value of IB. So IB, that can be calculated. It will be having another part. So that part is called as circulating current. You could note here that here sign what you are getting, that is negative, and here the sign which you are getting, that is basically positive sign. So now you are having IA and IB. So the total current I, that can be calculated now. Just substitute the value of IA and IB. So you will get the value of I. So I can be determined. Just you need to do some simplification after getting the value of IB. Then what we have done, after writing this, you can basically again simplify it, so you will get this expression. This is for our convenience only. Then the total load current, that will be the sum of IA and IB. So just you can add it, you are going to get this expression. So this you will get it. Then the terminal voltage, that can be determined. It will be given by V equal to I into Z. So you are having the value of I, substitute that value here, multiplied with Z, and do the simplification. You are going to get this expression can be obtained. So the circulating current, in both expression we have seen that current we have shown there. So the same is written over here, that is EA minus EB divided by ZEA plus ZEB plus ZEA into ZEB upon Z. So if you would notice, in both the expression the current that is same. So here you could see that this was your circulating current, and in here it is the circulating current. So both are same here basically. So that will be your circulating current. In this case the terminal voltage it can also be obtained in a different way. So V into IZ, the I is nothing, that is the sum of IA plus IB. So IA that can be written EA minus V upon ZEA, and IB that can be written EB minus V upon ZEB, and this Z that will come directly here. So just simplify it, you are going to get this value. We can write this in this manner: V multiplied by 1 by ZEA plus I by ZEB plus I by Z equal to EA divided by ZEA plus EB divided by ZEB. Suppose there are more than two transformers which are connected in parallel. So what you can do, you can write this expression in this term. So just you need to add their equivalent impedance here. Inversely it will be added, and the voltage that will be added in this one. So particularly if you talk about this particular expression, so that is applicable to any number of transformer, or you can say generators, which are connected parallelly. And this particular expression you could say that is called parallel generator theorem. So it is called as parallel generator theorem. Okay, if suppose you are interested to express IA and IB in terms of current I, then we started with begin this lecture with two expression. So we are going to consider those two expression, and they could be utilized in order to obtain this one. So from those two expression A and B, we are going to equate it, and from here we can get the value of IA ZEA, which will be equal to EA minus EB plus IB ZEB. Now what we will do in this, we are going to add IA ZEB on both sides. So we are going to get this expression. So ultimately our intention was to obtain IA and IB in terms of I. That's why we have added IA ZEB into this one. So what ultimately we are going to get it, we are going to get it this IA plus IB can be replaced with I. So now we can get the value of IA in terms of I. So by utilizing this, we are in position to get the value of IB in terms of I, and IA in terms of I, and IB in terms of I. So this would be the expression for the case. You could see that if suppose EA is equal to EB here, if EA is equal to EB, so what it will do, it will reduce this equation to earlier what we have seen, for which load current IA was shared by transformer A and B was computed basically. So that would be the earlier expression when EA is equal to EB. If suppose EA is greater than EB, then the current shared by transformers, that is transformer A and B, that will be given by, you can say, this expression, that will be given by this expression when EA is greater than EB. You could note that what we have considered, that EA is greater than EB, that was assumed. So IA that will be more than IB. Okay, so that observation you will find out that you could get it from this expression basically. So the circulating current is equal to the difference of EMF divided by the local circuit impedance. That is about the circulating current. So now we are going to take numericals. We will try to understand what we have studied, the parallel operation of transformer. So let us consider here one numerical. two transformers have equal voltage ratio, the magnitude of their equivalent leakage impedances are equal, but their reactance to resistance ratio are 9 and 3. Find the ratio of full load kVA delivered to the sum of their individual kVA ratings. So in this question, two transformers are given and the condition is given they are having equal voltage ratio. So the transformers, they are having equal voltage ratio. What else here is given? It is given the magnitude of their equivalent leakage impedances are equal. The magnitude of their equivalent leakage impedances are equal, but their reactance to resistance ratio are 9 and 3. It means their reactance X to R ratio that is not equal. So this is the case 1. Try to recall what we have studied in first case. So this question belongs to the first case. So what we will do, we are going to refer this phasor diagram particularly for this in order to solve this question. Okay, so I think the question is quite clear to you. What we have to determine here, we have to find the ratio of full load kVA to kVA delivered to the sum of their individual kVA rating. So what we have to calculate here, we need to calculate first full load kVA delivered. So what will be the full load kVA delivered? Try to recall the circuit diagram where your load was connected. So load is if having the impedance of Z, you can say, and the current is I and the voltage is the V. So kVA delivered, that will be V into I. So V and I multiplied by, in order to get the kVA basically, so you need to multiply with 10 raised to minus 3. Then sum of kVA ratings, individual kVA ratings. So what would be the suppose you are having transformer A and transformer B. So for transformer A, what would be the kVA rating? It will be V into the current which is shared by transformer A. Suppose it is IA. So V into IA into 10 raised to minus 3. That will be for transformer A. For transformer B, it will be V IB into 10 raised to minus 3. So you can add it. So this ratio has to be determined. Okay. So what we will do, what we need to do, it means we have to calculate the value of I. We are interested to calculate IA and IB. It has to be calculated. Okay. So these things, three things we are going to determine in order to determine the kVA. That is the I has to be determined, IA has to be determined, and IB has to be determined in order to solve this question. So what we will do, we are going to calculate first the angle phi B minus phi A in order to determine the value of IA. Okay, so the phi B and phi B minus phi A, that is the angle between the IA and IB. Okay, so in this case, just try to recall that what we have assumed that this IA and IB, that would be basically equal. Okay, so IA and IB, that will be equal here because their equivalent leakage impedance, they are equal. So the IA and IB, that will be equal. So first we are going to calculate this phi B minus phi A. So it will be given by tan inverse XEB by REB minus tan inverse XEA divided by REA. So its value is given, basically the ratio by X to R for both the transformer is given. So we are going to substitute the appropriate value. So we are going to get this angle phi B minus phi A, that will come around 12.10. So here 9, that is indicating the resistance to reactance ratio for first transformer, and the 3 it is indicating for the reactance to resistance ratio for second transformer. Okay, so here what we have noticed, what is given, that ZEA is given equal to ZEB, so your IA that will be equal to IB. So from this figure we are in position to determine the value of current I. So what would be the value of I? That will be basically given by this expression, that will become 2IA cos phi b minus phi a divided by 2. So from this figure you could see that the value of current will be basically, you could calculate from here. So just you can draw here what would be the value here. It will become I by 2. So you can calculate, you can consider this triangle and you can determine the value of I from here. Okay, so that can be calculated. So what you need to do, already you have calculated this angle phi b minus phi a, it has been calculated. So divided by 2 it will give you 6.06. so you can substitute that value here. So you are getting the value of I in terms of 2IA. So you got the value of total current in terms of IA. So here what you could do, here numerical sum of 2IA and phasor sum of I, its ratio can be basically determined. So what you will find out that it is equal to approximately equal to 1. So what we could conclude here, that the numerical sum of IA and IB, that is nearly equal to their phasor sum I. So this particularly shows that parallel connected transformers, the requirement of keeping reactance to resistance ratio equal is not of much importance. While discussing the conditions which is required for the parallel operation, there we said that okay, deviation is permissible. There are essential conditions, certain conditions are desirable conditions. So whatever is the essential condition, that must be fulfilled. The desirable condition, try to fulfill as much as possible. So in one of condition it was there that reactance to resistance ratio that should be equal. So it is not of that much importance. Let us come back to the question. So we have to determine the full load kVA delivered and sum of their kVA ratings. Its ratio is required. So we are having I. So we can get VI into 10 raised to minus 3 divided by sum of their kVA rating. We are going to write VIA plus VIB into 10 raised to minus 3. So from here you can cancel out V and V. So it will be the expression that will be in terms of I into 10 raised to minus 3 divided by IA plus IB into 10 raised to minus 3. Because IA and IB that is the same, so you can consider it as 2IA. This 10 raised to minus 3 also, that is going to be get cancelled. So just substitute its value. You are substituting the value of V, the I. So that is 2IA into this one cos 6.07, or you can directly substitute this value. So ultimately you are going to get cos 6.07 degree. So it is 0.994. So this will be your solution to this problem. Now let us consider another problem. In this problem the statement is two single phase transformers rated 1000 kVA and 500 kVA have per unit leakage impedance, it should be impedance not impotence, of 0.02 plus J 0.06 and 0.025 plus J 0.08 respectively. What is the largest kVA load that can be delivered by the parallel combination of these two transformers without overloading any one? So let us revisit this question again. What is given? There are two transformers. One is of 1000 kVA, another one is of 500 kVA. Their per unit leakage impedances are given, which are different. You could see here. So the question is here, what is the largest kVA load that can be delivered by the parallel combination of these two transformers without overloading? So what exactly we have to calculate? We are going to calculate the total kVA load, so that we could, for first transformer 1000 kVA transformer and for 500 kVA transformer, we are going to calculate the total kVA load, and on that basis we are going to conclude that what would be the largest possible load on transformer. Okay, so let us start this question. Let us begin with this question. So we are having two transformer, 1000 kVA and 500 kVA. So first what we are going to do, we are going to consider this the impedance which is given, basically 0.02 plus j 0.06. okay, it is given in per unit basically. So we have to choose here one of common base. So for first transformer, the leakage impedance is given this much. For second transformer, the leakage impedance is this much. So what we are going to do, we have to convert this into actual value. So we are going to choose a base. So here we are selecting, suppose the base is 1000 kVA. So in that case, the ZE1, that will be given by this value for the base, for the selected base. So we have converted this into basically from rectangular to polar form, and for the second, the base would be 1000 actually kVA, so its value is going to change, and then we are going to convert it into the polar form. So you are going to get this value. Then because in order to determine the kVA, total kVA load which is delivered by first transformer, kVA which is delivered by the first transformer, so we need sum of this ZE1 and ZE2, so that is already calculated for our convenience. Then we are interested to calculate the total kVA load for the first transformer. So we are going to utilize this expression, that is S1 equal to ZE2 divided by ZE1 plus ZE2 into total kVA load. So from here we are going to determine the value of S. So here substitute the appropriate value. So for first transformer, the S1 is given 1000 kVA, and ZE2 already we have calculated, and the sum of the per unit leakage impedances, that is actually, it is sum has been done. It is not in per unit form, but it is converted into respective base. Okay, so you are going to get this value, 1377.44 kVA. Similarly, you can calculate for another transformer, that is for 500 kVA. Substitute the appropriate value, you are going to get this value, 1825.3 kVA. So on per unit basis, you could see that the ZE1, that was given this one, based on its own kVA rating, which is less than ZE2 based on its own kVA rating. So what we can say here, we can say that as the load on parallel operation increase, the transformer 1 reaches its load of 1000 kVA first. So the first transformer, that is going to share 1000 kVA first. So the second transformer, how much it is going to share, that will be the total value what we have obtained, that is 1377 kVA approximately minus 1000. So the remaining would be the transformer 2, that is going to share basically the 377.44 kVA. So what is the therefore largest possible load on 2 transformer? That will be basically this value, 1377.44 kVA. 1377.44 kVA. So it is the largest possible load on 2 transformer. So this is the solution to the problem. So we are going to stop here. Thank you very much.